All right, so we are going to talk about risk and probability in water resources, which is probably one of my most favorite topics. I really like probability. So here we go. So most of you, I think, have already taken the statistics course, correct? Can you give me a thumbs up
Yes.
if yes?
Yes.
Okay. And that was the one, and that was geared towards civil engineers, hopefully 112, I think, right? So I'm hoping that some of this is a review. The last time I taught this, students had not taken the class yet, so it was harder. Okay, so we're going to start by talking about a probability distribution, and we've kind of already seen this with our rain and our storms. So a lot of the language is going to be the same. We're going to use we have 5-year rainstorms, we have 5-year floods, we have 100-year rainstorms, we have 100-year floods. It's a similar nomenclature. But this figure just shows a probability distribution. And just to help you think about this, you could basically plot you could do a similar thing that you do for rain, and you look at, say, 100-year record, and you find the max flow in each year, and then you see how often each one occurs, right? And so the way to read this is, and this figure is from Gupta, so if you have Gupta, you can find this figure. For a discharge of 700 CFS, you have, I'm going to read to the right, about a 45% chance that that flow rate would occur. Okay, so I kind of just like picked the peak here. And that's not the peak flow, that's the peak in probability. And then anything over here on the extreme left-hand side, that's going to be like a drought. So when we talk about probability distributions, we could also talk about like a 100-year drought versus a 100-year flood, which is going to happen on this right-hand side. But we're going to concentrate, because the books are more geared toward, and I think the understanding is easier to understand when we talk about floods, because floods are easier to see visually when you look at like how much flows in a river than the other side with droughts. Okay, so we're going to concentrate on floods, but just know that if you do this analysis, you could use a very similar thing to quantify droughts and say how common the drought is. Make sense? Okay, so if you have any questions on any of the slides, you can drop them in, well, you can put them in the chat, or if you're also looking at the slides, you can drop them in the slides. I don't know how easy that will be for you. Okay. Another way we can look at a probability distribution is to look at a cumulative probability distribution. And so this has the same information, but it is presented slightly differently. It is, you can look at it two ways, the two curves. You have either the probability that you will exceed some level of discharge, and the probability that you won't exceed some level of discharge. Okay, so if I'm following, again, this red line, which I put at about 700 CFS or CMS, the probability that you, if I get to this curve first, the probability that you do not exceed that flow is about 15%. And the probability that you do meet or exceed that flow is, those should add up to 100%. So, you know, my curve could be my straight line is probably not super straight. So if I said this was 15%, that would be like 85%, but that's not really what it's looking like. But they should add up to 100%. Okay, so it's just like adding it as you go. So again, hopefully this cumulative probability is a review from your statistics class. And we're going to come back to these curves because we're going to create our own probability curves in many different ways. But before we do that, we have to try and understand a little bit about probabilities and how we can estimate probabilities for flows. Okay. So to do that, we are going to look at what is called a binomial distribution. Have you heard of this? Or sometimes it's called a Bernoulli trial, and a Bernoulli trial makes up a binomial distribution. Was this covered in 112? Nice. Awesome. Okay. So I'm getting thumbs up on this. Great. So a binomial distribution or a Bernoulli trial is basically the best way to think about it is flipping a coin, right? So when you flip a coin, you either have success or failure. You either have heads or tails. There's only two possible outcomes. Usually we think of it as success and failure. Every time you flip a coin, the observation is independent from the previous coin flip, right? So if I do heads, I'm going to flip again. You don't know if it's going to be heads or tails. They're independent. When you use a binomial distribution, you're going to fix the number of, for example, coin flips. And then number 4, I did these a little bit out of order, is that the probability of success is the same for each one, right? So we have a fair coin. Each time we flip the coin, there's a 50% chance. And we're gonna go through a little bit on coin flipping before we bring this back into flood flow, how to translate it to flood flow. Okay, so I would like you all to take out a coin, and I didn't even bring one for myself. Toss it 3 times, and then in this slide, I want you to just, so I'm gonna exit out of here so you can see. Oops. Like let's say I flipped my coin and I got tails, tails, heads. I came into one head and typed in tail, tail, head because that's the order I did it in. Okay. So flip a coin 3 times. Try to actually do it and not just like pretend you're doing it. And put in this row, the combinations row, what you get. Try to see how many people are here so I know when everyone's done.
Dr. Doyle, I got on a little late. Where is this slide?
I will drop it in the chat one more time if I can find my chat. There you go. Check your chat.
Thank you.
All right, so there's 12 up here. Looks like there are 15 people on the call, so I'll give you another like 10 seconds here. It's a lot of all tails. Okay. Okay, so I'm just going to total these up. So we got 4 times where there were 0 heads, 3 times where there was 1 head, and then 1, 2, 3, 4, 5 times where there was 2 heads and 1 time where there was 3 heads. So our total there is 4, 7, 8 is 13. So then we can figure out percentages. And if someone has a calculator nearby or another window up, I don't know, I guess I could do it. But we want to basically, if someone can help me fill these out, I'm just going to do what's 4 over 13 and do that as a percentage. Can someone go from the other?
I think it needs to change column 1. There's 2 heads in column 1, so it needs to be 2. Just switch that over.
What?
Does that make sense?
No.
And the number of heads for 1.
Got it. Right here. That one's in the wrong spot.
Yeah.
Yeah. Okay. So there's 6 of 2 heads and just 2 of 1. Okay. So, but we still have 4, 5, 6, 13 total. So 4 out of 13 is about, I'll call that 31%. 2 out of 13 is 15%. 6 out of 13 is 46%. These are probably not going to add up to 100. 1 over 13 is, call that 8%. Does that equal 100? It does. Amazing. Okay, so here are our results. According to our trial, 31% of the time we'll get 0 heads, 15% of the times we'll get 1 head, 46% of the time we'll get 2 heads, and 8% of the time we'll get 0 or 3 heads. Let's look at this more mathematically now, okay? And think about all the possible combinations that you can get for 0 heads. What are they? There's really just tails, 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 right? That's the only way to get 0 heads. To get 1 head, you can either do first your head and then 2 tails, or tails, heads, heads, or tails, tails, heads, okay? Similarly, if you get 2 heads, you could have heads, then tails, then heads, or tails, then heads, then heads, or heads, heads, tails. And then if you want 3 heads, there's 1 way to get it. Okay, so what are these totals? You have 1 way to get 0 heads, 3 ways to get 1 head, 3 ways to get 2 heads, and 1 way to get 3 heads. These percentages, we have 8 total ways that you can flip the 3 coins. So this is 12.5%. This is 3 over 8 is 37.5%. 37.5%. And then 12.5%. Okay, so I'm going to just copy over really quick what we got on our trial. So this was our trial. And so we can compare and see, okay, in our trial of the 13 of us that flipped the coin, we got 31% get 0 heads. And we don't know why that happened. Maybe we had some unfair coins or some unfair flips. But it was not really what we expected, right? We expected closer to 12.5%. The closest 2 were probably the 2 heads and the 3 heads. So we could, yeah. So now we're going to figure out the same thing that we just did, where I went through all the combinations, because you can imagine now if you have like, let's say I flip the coin 20 times. We don't want to necessarily have to make these combinations and count them all each time. So we're going to use math and statistics stuff to do it. okay? And that's where we get into our binomial distribution. I'm gonna stop here and just ask if there's any questions so far. This is much more fun live when I just bring in coins and make you all flip them. But this is better than nothing. Okay. All right, I don't see any hands up, so I'm going to assume that we are all good. I'm going to move on to the next slide. Okay. So we kind of already talked about this when we have a binomial distribution, which is made up of Bernoulli trials. Those terms are often interchanged when we're talking about it and reading about it. We're going to have the probability of an event taking two discrete values, either true or false, or heads or tails. And the probability of each event is independent of time or past occurrences, right? So this is, again, the same with floods. So when we talk about a flood or a storm, every time it rains, so like supposedly we're going to get rain next week in San Jose, it does not matter how much it rained the previous day or the last time it rained on how much rain is going to come this time, right? So each day is its own independent event that does not depend on previous events. That may not entirely be true in floods and atmospheric science anymore, but that's still the model that we use. And it's probably okay for the number of data points that we use. So this allows us to use a binomial distribution. And so the equation for this is here. So the equation says the probability of X, I'm going to get my annotation here, is equal to this funky term, okay, which is called the binomial coefficient. And so it's written as these big parentheses with the n on the top and the x on the bottom. It's not missing a fraction. That's just how it's written. And then we have p to the x and q to the n minus x. So this binomial coefficient can be calculated as n factorial divided by n minus x factorial times x factorial times p to the x times q to the n minus x. Okay, so n is the total number of trials. So in what we just did, n was 3. We had 3 flips of the coin, so our n was 3. X is the number of successes that we're looking for. So for example, when we were seeing how many times we got 0 heads, our x would be 0. P is the probability of getting a success in one trial. So with a coin, that's 50% for heads. And then Q is 1 minus that, which is the probability of getting a failure. So it's also 50% for a coin flip. Okay, does that make sense? So that, again, the sort of math behind this, it goes back to statistics, and it's called permutations and combinations. It's like really fun if you want to get into statistics, but I will just let you know that this is the equation. Okay. All right. So that's our equation. Let's look at how to apply it to our coin toss. First, I got to clear. There's so many buttons to push. First, I saved like my annotation. So I have a picture of this, and I'm going to clear it. I'm going to clear the drawings. And then I am going to hit that button and then go to the next slide. Okay, so let's look back at our coin toss and use these equations. And I'm going to attempt to write on my screen. It's going to be really messy, but that's okay. So to use this equation with my coin toss, let's look for the probability for 1 head in 3 tosses, which we already know should be 37.5. Okay, so I'm just going to write that number there. So when we do the math, we can compare what we have. It's like a whole nother skill to write with your mouse and also hitting the button. So this looks like worse than my kindergartner's penmanship. Anyway, so if I have 1 head in 3 tosses, what is my X? So I need to define these 4 things. I need to define X. I need to define N. I need to define my P and my Q.
I think X would be 1 and N would be 3, right?
Yep. So X is 1. X is the number of successes that we're looking for. N is 3 because that's the number of trials that we're going to do in total. Our P is the probability that we have success in each trial. For a coin toss, it's 0.5. Okay. And then our Q, sometimes this is written in the equation as 1 minus P. Just depends on who wrote the textbook or the web page you're looking at. And this is also 0.5 in our example. Okay. So the binomial coefficient, which is also, by the way, the total number, possible number of outcomes we can get, is equal to 3 factorial divided by 1 factorial times 2 factorial equal to 6 over 2. That is a terrible 6 over 2, which is 3. So what this means is there are 3 different ways that you can get 1 head in 3 tosses. Okay, and we already showed ourselves that a couple slides back, right, when we made that table. Okay, so the probability that you get 1 head in 3 tosses, I'm going to write it like this, is equal to that coefficient that we just found, 3, times 0.5 to the 1 power times 0.5 to the 2nd power, which is 0.375. Okay, which matches what we saw previously when we just counted all the possible ways that you could flip 3 coins. So this shows us that this math works, okay? So I have a question for y'all. What does, if I said, okay, so the probability that I have 1 in 3 is 0.375. If I did 1 minus the probability of 1 in 3, you would get, what is that? 62.5, right? Okay, so the probability that you don't get 1 head in 3 tosses is 62.5%. But what does that like mean? If I don't get 1 in 3 heads, what does that mean?
Mean that you're getting tails then?
Does it mean I'm getting tails? Well, it means I'm getting at least, well, maybe, but maybe not.
Doesn't that mean that it's literally anything but 1 head in 3 tosses?
Yeah, exactly. So it means that I'm getting not 1 head in 3 tosses. So you could be getting 0 heads, you could be getting 2 heads, or you could be getting 3 heads. Does that make sense? Yeah, so it's important to think about what the opposite of what you're asking for means, because sometimes using the opposite is easier. And we'll come back to that. Okay, any questions on this slide before I move on? Okay, I'm going to save this scribble. Then I'm going to clear it. And then I'm gonna hit that button. All right, so coming back to that a little bit, this was the heads and tails I found online, generator of heads and tails. So if you have two mutually exclusive events, A and B, so that could be flipping two different coins, for example, and they both have certain probabilities, I want to know the probability of getting either A or B. Okay, between A and B, with probability A and B, what is the probability that you get either A or B? That's the first thing I'm going to ask. I didn't type this out quite right, but I can write it out. Okay, so what is the probability that I get either A or B? These are just formulas for this type of event. We write this as probability of A with a line B. Hopefully that looks familiar from statistics. This is the probability of A plus the probability of B. Okay. If I want to know what happens if I get the probability of both A and B together, this is written as the probability of A and B. We write this as like a U, it's like an intersection kind of, and we find this is the probability of A multiplied by the probability of B. And then we talked about this one. The probability of something not occurring is the probability of not A, which is 1 minus the probability of A. Okay. So again, these are just formulas and we will use them. Any questions? Okay. Save that. Then I clear my drawings and I have to hit the annotate button. All right. So now we're going to think about how this relates to hydrology, to water resources, to floods, droughts, whatever. So we're going to think about heads as some particular level of flow happening. If you want to think back to the beginning of when I started this lesson, let's say it's 700 CFS. So heads is that flow, 700 CFS occurred. Tails means that flow did not happen. Okay, so success, the flow happens. Failure, the flow does not happen. Well, how do we think about that in terms of what we know about like 50-year storms or 100-year storms? So let's say we have a fair coin, which would be a 50-50. Okay, so 50% chance you get ahead, 50% chance some particular flow happens, 50% chance you get a tail or some flow does not happen. This translates to a 2-year storm. Okay, so same as we did for rain. But that is not we usually don't care in water resources. Well, we do care about 2-year storms. It's usually used as a design consideration. We look at the amount of rain. We want to basically design for, like, when we're designing drainage systems, we want to design for something that occurs frequently. So a 2-year storm is often used. And really you have a 50% chance that happens in any given storm, okay? But when we're looking at extremes, you may be actually looking at a 10-year storm, which means that your head, or your P, if we're thinking back to the formula, is 10%. There's a 10% chance that it'll occur and 90% chance that it will not occur. And again, that 10% chance means there is 10% chance that exactly, for example, 700 CFS will occur, and then 90% chance that some other flow occurs. It could be more, it could be less. That's not what we're talking about here. We're only talking about that particular flood occurs, okay? So that's how you translate this head and tails to hydrology. So now what's changing is, instead of having a fair coin where every time you flip it, you get 50-50, it becomes an unfair coin, and usually to your disadvantage if you're thinking about heads being a success. However, if you're trying to prevent floods, then, you know, maybe we don't want the heads to happen. Does that make sense? Does somebody want to try and reiterate what I just said so that it can, someone else, y'all can hear it in someone else's words?
The way I get it, it's like a weighted coin when it comes to hydrology, right?
Mm-hmm. Yeah, exactly. It's like a weighted coin, but the formula we're going to use is the exact same. It's just that our probabilities are different. Okay, so I think the best way to think this through and kind of understand a little bit better is to do some examples. That's what we got going on next. So how many of us are in K15? What I'd like to do is give you a couple of minutes here to try and think this through. And what I'll let you do is go to this slides, and when you think you have an answer, just type it into the Google slide, okay? And then we'll go through it. So you can just type your answers in here. Okay, so we're on the right track here. It is going to be 1 minus the probability of a 5-year storm. But we know already the probability of a 5-year storm. The probability of a 5-year storm is 20%. So the answer is 80. That is correct, whoever typed that in. Okay, so a few things here. So let me present this, and I'll do the math as well. But so the probability of not seeing a 5-year storm is, again, going to be 1 minus the probability of a 5-year storm, because of that not, and the probability of a 5-year storm is 1/5, which is 0.2. So the probability of not having a 5-year storm is 1 minus 0.2, or 80%. Okay. That doesn't tell us if, you know, you're going to see a storm bigger than that or smaller than that. It only tells you that you're not going to see that 5-year storm. Okay, that was a warm-up, easy one. Let's clear my drawings, and then we'll go to the next one. Okay, so I want to know now, in a 3-year span, what's the probability that a 5-year flood occurs exactly one time? So this is going to look familiar to the coin toss. Okay, so previously we did 3 coin tosses. Now we're doing 3 years, so that's similar. We looked what would happen, or the probability that you would get 1 head. This time we're seeing what happens when you get exactly 1 5-year flood. So if I look at this equation, I'm just going to ask each, so y'all can unmute yourselves for 2 seconds. So there's some way I can unmute you all somehow. Anyway, is n going to be the same that we did previously? Is n 1?
Yes.
Yes.
Yes. Awesome. Is x still 3?
Yes.
Yes. Is our p still 0.5?
No.
No. What is our p?
It's 20%.
Yeah.
Or
So
it's
now our
0.2.
p is 0.2. And is our q 0.5?
No. It's
No.
0.8.
0.8. Right. So we should be easily able to write this equation. The probability that we get 1 5-year flood in a 3-year span is going to be equal to 3 factorial, that's our n, divided by 1 factorial, that's our x, times 2 factorial, that's our n minus x, times 0.2 to the 1, times 0.8 to the 2. That looks terrible. That looks slightly better, which is 0.24, or 24%. Okay, so each year you have 20% chance of seeing a 5-year flood. In 3 years, you only have a 24% chance of seeing a 5-year flood. So it's not like it adds up 20%, 20%, 20% to be 60%, which is a lot of, I think, what people think, like a 100-year storm. Oh, well, we just saw a 100-year storm, so clearly our counting starts over again and we're not going to see it this year. But that's not true. Okay, so real quick, I'm just going to write out, so if you come back to this later, you'll know what we use. So our x in this case was equal to 1. Our n is equal to 3. Our p is equal to 0.2, which is 1/5. So that's based on what we know from our 5-year storms or 5-year events. A return period, that's the word I was looking for. And our q, which is 1 minus p, is 0.8. Okay. Any questions on that one? All right. So I'm saving, each time I write on my screen, I'm saving a picture of that. So I'll make sure to post those as well when this is all over. Okay. This one is a slightly more complicated, maybe. And I want to know, in a 3-year span, what's the probability that a 5-year flood happens every year? So give you a couple of minutes, maybe think about this. And if you think you know the answer, then you can hit your raise hand button and I'll see. Can tell even less on Zoom if you're doing what I ask or on your cell phones. What's X?
3.
3.
3. What's N?
3.
3. What's P?
0.2.
Yep. And what's Q?
0.8.
0.8.
Yep. Okay. So this one just changes a little bit from our previous example. So now I'll still write the whole thing out though, so we can all have it. The probability that you get 3 5-year floods in 3 years is equal to 3 factorial divided by 3 factorial times 0 factorial. What's 0 factorial equal?
1.
Yep. Times 0.2 to the 3rd power times 0.8 to the 0 power. And this is equal to 0.08. So you have an 8% probability that you get a 5-year flood every year for 3 years in a row. Okay. Any questions on that one? Okay, this next one I think is going to make you think a little bit. So now I want to know, what is the probability of a 100-year flood in either 2013 or 2014 or in both years? So I'm going to tell you that to approach this, we're going to have 2 different probabilities and we're going to add them together. Okay. So what do you think these 2 probabilities are?
There's the probability of like 100 years flood in 2013 and 2014 for each.
Yeah, so you said, first you said and, which is like both, right?
Right.
Okay, so that would be the probability that you have 2 100-year storms in 2 years. And then how do I capture this one, the probability of either 2013 or 2014?
Would that be 1 and 2?
Yep. So this would be the probability that you have 1 100-year storm in 2 years. It doesn't matter what year it is, right? Okay, so let me just do this. So again, if you look back at this later, you'll know. Okay, so to do that, you are going to do, we'll write this out. So you'll have 2 factorial divided by 1 factorial times 1 factorial. Our P is 0.01. We're going to erase that to the 1 power times 0.99 Are there professors who write on a real whiteboard this messy? Maybe. Okay, then I'm going to add to this 2 factorial divided by 2 factorial times 0 factorial times 0.01 squared times 0.99 to the 0. And this is equal to 1.98%. I'm writing these as percentages, plus 0.01%, which is 1.99%. Okay, so there's about a 2% chance that you could have a 100-year flood in either 2013 or 2014 or in both. Does anyone see an easier way I could have solved this?
Could you have solved the probability of them not occurring and then subtract that from 1?
Yeah, so we could have done, so if the probability of it not occurring would be the probability, let's write this, probability of no 100-year storms, right? Because in 2 years, because we're either doing 1 within the 2 years or 2 in the 2 years. So we could have solved that the same by doing 1 minus the probability of 0 in 2 years, which is a little bit easier to solve. You just do 1 minus 0.01 squared, which is 1.99%. Okay. So the probability that there is not a 100-year storm at all during a 2-year span is basically 98%, 98.1%. And so you do 1 minus that to get that probability. Any questions on that one? Okay, one more to go. All right, so now we have a stormwater system designed with a capacity for a 10-year recurrent storm. So our probability, our P is 0.1. I want to know the probability it'll fail in the next 10 years, okay? And then I want to know if it was designed for the larger 20-year flow, what's the chance it would fail in the next 10 years? So first thing that we need to understand is what it means for a system to fail, okay? And we've kind of touched on this in the last problem, but the probability of failure means, what this means in this case, is that there's going to be one or more storm. I don't care how many. But if my stormwater system fails, that means at least we had one or more storms that was greater than or equal to that 10-year storm. And I don't care when I'm doing this calculation if that storm occurs in the first year, the third year, if it occurs in the second and third and fourth and sixth years. All I'm looking for is that there's one or more of those storms in the 10-year period. Okay, so we just did sort of this walkthrough in the previous problem. Okay, so the probability that there's one or more, which is the probability of failure, is equal to 1 minus the probability that there's none, right? So this is 1 minus 1 minus p to the n. Okay, so real quick, what do each of these things mean? The p is like, we're looking at a 10-year storm, so that p is going to be 0.1. My n is the number of years I'm looking at, so I'm looking at 10 years, so my n is going to be 10. Okay, so for this first part, so the probability it'll fail in the next 10 years, I'm going to do in blue, so I'm just going to underline this in blue. So this is 1 minus 0.1 to the 10th power, 65%. So there's a 65% chance that in the next 10 years, you are going to fail your system. So that means if you're a water resource engineer, you have to think about, okay, what am I designing? Is this like a parking lot? Maybe I'm willing to allow a parking lot to fail 65, have that risk of 65% failure, because it's not going to cost a lot of monetary damage. And so maybe a 10-year storm is the right design storm to use in that case. But if you're designing a drainage system around an apartment building, you probably don't want that to fail with the 65% chance that it's going to fail in 10 years because it's much more expensive to fix, right? So these are the kinds of risks that civil engineers have to think about. And I know I usually get groans, but you're all muted, so I won't get groans. But it's really cool to mix this with not environmental in this class mix well, but economics as well, because you can start to look at how much a flood would cost to fix. And then there's trade-offs. Like maybe I'm willing to let a parking lot flood and ruin all of the plants I put in, or the stores are willing to not have as many customers because their parking lot is flooded for a certain number of days and they don't want to go in the flooded parking lot, rather than pay for a higher level of protection. Okay, so it's all about these like trade-offs, and you can do all your fancy economic analysis to the side, and you can bring risk into it, which is kind of fun. Anything that involves math is fun, right? Right. Okay. So this week, actually, my 9-year-old had a breakthrough with math because she's been memorizing multiplication. And then this year they started calculating areas, and she was like, oh my God, I can use multiplication for something other than just my times tables. It's a miracle. And so that's my story. Okay, so for the 20-year flow, let's look at this. For a 20-year risk, okay, so now we're designing it for a larger flow, a 20-year flow, and I want to know how much it'll fail in the next 10 years. So this is going to be very similar, but the only thing that's going to change is my P. My P now becomes 0.05. So for a 20-year storm, I'm going to do 1 minus 0. Oh my God, that was terrible. 0.05 to the 10, which is 40%. Okay, so again, how much more will it cost to design, whenever you're designing your stormwater system, to a 20-year event instead of a 10-year event? And is that 25% probability savings enough to justify the increase in cost? Okay, so these are the types of things we get to think about as engineers. Okay, that is all I got. Do we have any questions about anything? Probability or the environment or water, whatever.
It has like, so I know the city like separates certain areas into flood zones. Is that based off of the year flows or based off of like the geographical like location?
Oh man, 100-year floods. Those are so cool to look at. Basically, it's all based on, you're in a floodplain if you're in a 100-year flood event area. And that is based on a Army Corps and USGS like mapping the storm events, and we'll kind of start getting into that a little bit more in this class. But it's like the closer you are to a river, the more likely you'll be in a 100-year storm event. So
Okay.
if you live in a flood zone, you're required to have flood insurance.
Okay, that makes sense. Because the lot that I'm working on for senior design, it's in flood zone Z or D, but it doesn't have any like requirements for like stormwater pollution prevention plans.
Yeah, because the flood zones are more about like how high the river is going to rise.
Gotcha.
If
Okay.
there's a flood event.
Okay.
Pretty much every storm, all of our storm drains have the same impact on the rivers, like pollution wise. Because they all go to the same place. All right, anything else? So I did extend the due date for bonus material for infiltration. I don't know if I typed that in my last email announcement. Till Monday. I got a few people asked since most of you had your midterm today. So if you're still interested in doing some bonus stuff, you can look at that. I'm trying to add a few more like easier bonus things to do. I should just throw up some more, like find an article related to water resources. So I'll do that probably this afternoon. And I'm going to keep populating this next module, which is all about peak flows. So we're starting with probability, and then we move into some other ways to find peak flow, including, so I'll say this now so you can reactivate this part of your brain that you should have learned last quarter, which is the rational method. Does that sound familiar? Yay. Okay. So I think you probably did the rational method in 125, right? And so
I don't think we learned it, Dr. Doyle.
no.
Yeah, I take back my thumbs up.
You didn't use Q equals CIA?
Like vaguely.
Oh, we
Vaguely.
called it something else, I think.
Okay.
Oh, I think we did that in geology.
Oh, really?
Yeah, that was a while ago.
We talked about it in geology in a WOPS class, and then last quarter with Aria too.
Oh, okay. But you didn't do it in 125?
Which class is that one?
That was municipal.
That was municipal.
Yeah, with
And
the
you
WOPS.
And you didn't have to like in your AutoCAD thing like design the storm drains and their sizes?
No,
we did have to do that.
We did,
You
but
did.
We were
our
supposed to.
team told us how to
Yeah,
learn it.
that was a confusing time.
Okay, well, hopefully we'll cover it and you'll look back. It's basically how to find like how much rain falls on like a roof and how long it takes to get to the storm drains. So we'll cover it and it'll be fine. But okay, it's good to know that you all mostly don't remember it. So yeah, we'll do that, and then we get to do something called unit hydrographs, which are really fun. And then we're going to route the flow through anyway. I really nerd out on this stuff. So, and we only have 4 weeks to go in the quarter, so that's crazy. Okay, so I will be around this weekend if you email me, but probably not Sunday as much because it's Mother's Day. So don't forget to call your moms or give them the day off if you're at home with them. And that's about it. Any other questions? I'll stop recording.